Welcome back to the Starting Out with Quantum Computing podcast. So this week we're looking at quantum error correction, a pathway to useful quantum computing. So quantum error correction is the art of reverting the errors in qubits, or for short you can think of it as QEC. But how does it work and why is it effective? So quantum computers today have very high error rates, some as high as 1 in every 100 operations. So that means every 100 operations there's one error. And the reason this occurs is because quantum bits, qubits, are very fragile in nature. And this can heavily restrict what tasks you can actually perform with a quantum computer. So to actively correct this on the fly, we can use quantum error correction and all the techniques within quantum error correction. So QEC is theorized to be one of the missing puzzle pieces in this long race for quantum advantage. But that's not to say that QEC doesn't exist, but rather that it is currently not effective enough to achieve fault-tolerant quantum computing. So QEC, what it does is it protects the quantum state from being altered due to errors, which can be caused by decoherence and quantum noise. And previously, I wrote about decoherence, so check that out if you want to understand more about the things that break quantum states. And so if we can correct these errors, then we can, even if we have operations on a quantum computer with low fidelity, i.e. they're not faithful and sometimes they work, sometimes they don't, we'd still be able to run complex algorithms and yield accurate results if we had good quantum error correction. And so, in a sense, quantum error correction is more realistic as it assumes a NISQ computer, NISQ, standing for Noisy Intermediate Scale Quantum Computer. These are computers that are of middle size, they still suffer from noise, they still suffer from errors, and quantum error correction assumes that. There are many approaches to reversing errors, and we're going to discuss a couple of them today. So the first error correcting code I'd like to talk about is the bit flip code. So unlike a normal classical computer, we can't simply just copy and paste our bits or our qubits repeatedly in order to save the state and to protect it. And this is because in the quantum world, there is the no cloning theorem. And this theorem states it's not possible to clone anything. It's not possible to make a perfect copy of any arbitrary quantum state. So therefore, we have to rely upon spreading this information out about one qubit amongst many. So, for example, we could spread the information of one qubit amongst 3 qubits. As proposed first by Asher Perez in 1985, we can simply use entanglement to achieve this spreading. So by entangling 3 qubits together, we can let this new state represent the abstract single qubit known as a logical qubit. So logical qubit is a type of qubit that's actually made up of many, but we'll use those many qubits to represent one qubit abstractly. So it's not actually a single qubit, but once we've made our logical qubit, we cannot simply just measure it to check whether errors have occurred in one of the 3 qubits, as this would incur wave function collapse, the collapsing of a quantum state. When I look inside Schrodinger's box and I check to see if the cat is alive or dead, it's no longer in the superposition of both alive and dead. It's definitely one or the other. So therefore, we don't want this, because we want to correct errors but not destroy the quantum state. So we have to make syndrome measurements with 2 extra ancilla qubits on the side. Syndrome measurements they're a type of measurement which doesn't affect the main qubits that you care about. And by performing these measurements on the side, we can infer where the error occurred within our main 3 qubits, making up the logical qubit, without actually measuring them directly. So we'll check for a property known as parity, and we'll ask whether one of these 3 qubits differs from the other. And so what this means, of course, is there are 4 possible outcomes from syndrome measurement. Either there's no error, either there's an error in qubit 1, either there's an error in qubit 2, or lastly, there's an error in qubit 3. So this is amazing because this tells us which qubits are different from the others without directly measuring and asking the quantum computer what the states of each qubit are, which would in turn force wave function collapse. However, we should note that this procedure only really works in the case where one qubit error occurs, this bit flip code. So if there's more than one qubit which has flipped due to error, then syndrome measurement will fail because it will show a different parity, and this will make us think that, in fact, there's another error that didn't actually happen. So even with that, even still, mathematically, we can show that using bit flip code has a higher chance of success, has a higher fidelity than using no error correction scheme at all, as long as the probability of qubit error is less than 50%, which realistically it should be. So moving on to phase flip code. So there are fundamentally two types of errors that can occur in qubits. Either the state of the bit can change, so 0 to 1, 1 to 0, or the sign associated with the state can change, minus to plus, plus to minus. And we do call the sign associated with the state of the qubit the phase. And do note that quantum systems can actually experience much more complex errors and different noise profiles, but this is a basic way of understanding error, that there are two types. So much like before in the bit flip code, we can apply the same reasoning and procedure in order to correct qubits that have had their sign flipped. The only difference is we need a certain type of quantum gate, and if you're not sure what a quantum gate is, I would recommend taking a look at our ultimate quantum glossary. But a quantum gate is basically a type of operation that we do on qubits. We require a quantum gate known as the Hadamard gate. This is a gate that is responsible for generating superposition. It is the gate that creates superposition. And this gate enables us to use the above procedure, the bit flip code, to correct errors in the signs of the qubits rather than the actual states of the qubit. So once again, this code assumes that only one qubit error has occurred, and we can also mathematically show that it will perform better than not having no error correction scheme, given the probability of qubit error is less than 50%. So, moving on to our third and final code, you can see where we're going with this, listener. After all, if we have a code that can correct the phase for phase flips, and we have a code that can correct for bit flips, could we have a code that can do both simultaneously? And of course we can. It's called Shor code, developed by none other than Peter Shor himself in 1995. And it is a complex circuit diagram. So the circuit refers to the layout of what instructions we perform on the qubits and in what order. But essentially there are 9 qubits. And the first qubit, the fourth qubit, and the seventh qubit are used to correct the phase flip errors. Meanwhile, the groups of qubits, 1, 2, 3 as one group, 4, 5, 6 as another, and 7, 8, 9 as another, are used to correct the bit flip errors. So what this means is that we use syndrome measurements to correct a bit flip within each block of 3 qubits, whilst on the other hand, we can simply just check the parity between just 3 of the qubits, 1 qubit in each block, to fix phase flip errors. And we make this distinction because if a singular qubit undergoes a bit flip error and its state changes from 0 to 1, 1 to 0, then that specific qubit must be corrected. Meanwhile, if a singular qubit undergoes a phase flip error, it changes the sign of the entire block of 3 qubits, meaning we can detect this by comparing the blocks of 3 and then simply reversing the phase error on any of the qubits. And this is one of the weird things about quantum states. If an entangled state undergoes a bit flip error, this affects the specific qubit solely. However, if an entangled state undergoes a phase flip error, this affects the entire entangled state. Either way, the Shor code is able to correct any single arbitrary error on a single qubit. Any more qubits succumb to error, and it cannot guarantee correction. So the question is, how well can we implement quantum error correction in real life? So funnily enough, QEC codes tend to introduce more error than correction. There are instances of incredibly high performing error correction codes, but generally QEC consumes resources and is qubit hungry. And so the point at which the error correction rate is equal to the rate of errors that accumulate within the quantum computer, this is called the error threshold. And it's a benchmark for which all quantum hardware companies aspire to surpass, or should I say, go below. The reason I say that is because above this threshold, the quantum computation is destroyed by errors, even with quantum error correction. But by going below the threshold in the error rate, quantum error correction can begin to actually work successfully, and we can start to scale our quantum computers to a useful number of qubits, perhaps even 10,000 qubits. And at this scale, at this number of qubits, useful quantum algorithms can be run without succumbing to error and can provide accurate solutions at faster speeds than classical methods. So the real question is not whether a quantum computer has error correction or not, but rather how far below the error threshold can the quantum computer go. Thank you very much for listening to Starting Out with Quantum Computing. If you enjoyed, please share with a friend or drop a comment. And I will see you on our next week. Bye-bye for now.